Welcome back. Whew, the last video was pretty full on. We did a fair few steps, but this is all good practice. The best way to learn PyTorch code is to write more PyTorch code. So did you try it out? Did you run this code? Did it work? Did we probably have an error somewhere? Well, let's find out together. You ready? Let's train our biggest model yet. In 3, 2, 1, boom. Oh, of course we did. What do we have? What's going on? Indentation error. Ah, classic. So, print out what's happening. Do we not have an indent there? Oh, is that not in line with where it needs to be? Excuse me. Okay. Why is this not in line? So this is strange to me. Enter. How did this all get off by 1? I'm not sure, but this is just what you'll face. Like sometimes you'll write this beautiful code that should work, but the main error of your entire code is that it's off by a single space. I'm not sure how that happened, but we're just going to pull this all into line. We could have done this by selecting it all, but we're going to do it line by line just to make sure that everything's in the right order. Beautiful. And we print out what's happening. Ready? 3, 2, 1, round 2. We're going. Okay, so this is the progress bar I was talking about. Look at that. How beautiful is that? Oh, we're going quite quickly through all of our samples. I need to talk faster. Oh, there we go. We got some good results. We got the test, the train loss, the test loss, and the test accuracy is pretty darn good. Oh my goodness. This is a good baseline already. 67%. So this is showing us it's about 7 seconds per iteration. Remember, TQDM is tracking how many epochs we're going through. So we have 3 epochs. And our print statement is just saying, hey, we've looked at 0 out of 60,000 samples. Then we looked at 12,000 out of 60,000 samples. And we finished on epoch 2 because it's 0 indexed. And we have a train loss of 0.4550 and test loss 4766 and a test accuracy 834265 and a training time about just over 21 seconds or just under 22. So keep in mind that your numbers may not be the exact same as mine. They should be in the same realm as mine, but due to the inherent randomness of machine learning, even if we set the manual seed, might be slightly different. So don't worry too much about that. And what I mean by in the same realm, if your accuracy is 25 rather than 83, well then it's probably something's wrong there. But if it's 83.6, well then that's not too bad. And the same with the train time on CPU. This will be heavily dependent, how long it takes to train, will be heavily dependent on the hardware that you're using behind the scenes. So I'm using Google Colab Pro. Now, that may mean I get a faster CPU than the free version of Google Colab. It also depends on what CPU is available in Google's computer warehouse where Google Colab is hosting of how fast this will be. So just keep that in mind. If your time is 10 times that, then there's probably something wrong. If your time is 10 times less than that, well, hey, keep using that hardware because that's pretty darn good. So let's keep pushing forward. This will be our baseline that we try to improve upon. So we have an accuracy of 83.5 and we have a train time of 20 or so seconds. So we'll see what we can do with a model on the GPU later and then also later on a convolutional neural network. So let's evaluate our model. Where are we up to? What we just did, we built a training loop. So we've done that. That was a fair bit of code. But now we're up to, we fit the model to the data and make a prediction. Let's do these two combined, hey? We'll evaluate our model. So we'll come back. Number 4 is make predictions and get model 0 results. Now, we're going to create a function to do this because we want to build multiple models. And that way we can, if we have, say, model 0, 1, 2, 3, we can pass it to our function to evaluate that model, and then we can compare the results later on. So that's something to keep in mind. If you're going to be writing a bunch of code multiple times, you probably want to functionize it. And we could definitely do that for our training and loss loops, but we'll see that later on. So let's go def eval model. So evaluate a given model. We'll pass it in a model, which will be a torch.nn.module or of type. And we'll pass it in a data loader, which will be of type torch.utils data loader. And then we'll pass in a loss function so that it can calculate the loss. We could pass in an evaluation metric if we wanted to track that too. So this will be torch nn.module as well. And then, oh, there we go. Speaking of an evaluation function, let's pass in our accuracy function as well. And I don't want L, I want that. So we want to returns a dictionary containing the results of model predicting on data loader. So that's what we want. We're going to return a dictionary of model results. That way we could call this function multiple times with different models and different data loaders and then compare the dictionaries full of results depending on which model we passed in here. So let's set up loss and accuracy equals 0, 0. We'll start those off. We'll go, this is going to be much the same as our testing loop above, except it's going to be functionized and we're going to return a dictionary. So we'll turn on our context manager for inferencing with torch.inference mode. Now we're going to loop through the data loader and we'll get the X and Y values. So the X will be our data, the Y will be our ideal labels. We'll make predictions with the model, in other words, do the forward pass. So we'll go ypred equals model on X. Now we don't have to specify what model it is because we've got the model parameter up here. So this is, we're starting to make our functions here, or this function, generalizable. So it could be used with almost any model and any data loader. So we want to accumulate the loss and accuracy values per batch, because this is within the batch loop here, per batch. And then we're going to go loss plus equals loss function. We'll pass it in the ypred and the Y, the true label. And we'll do the same with the accuracy. So, except this time we'll use our accuracy function. We'll send in yTrue equals Y and ypred equals ypred.argmax because the raw outputs of our model are logits. And if we want to convert them into labels, we could take the softmax for the prediction probabilities, but we could also take the argmax and just by skipping the softmax step, the argmax will get the index where the highest value logit is. Dim equals 1. And then we're going to make sure that we're still within the context manager here, so with torch inference mode, but outside the loop. So that'll be this line here. We're going to scale the loss and ACK to find the average loss slash ACK per batch. So loss will divide and assign to the length of the data loader. So that'll divide and reassign it to however many batches are in our data loader that we pass into our model function. Then we'll do the same thing for the accuracy here. Length data loader. Beautiful. And now we're going to return a dictionary here. So return, we can return the model name by inspecting the model. We'll get an attribute of the model, which is its class name. I'll show you how you can do that. So this is helpful to track if you've created multiple different models and given them different class names. You can access the name attribute. So this only works when model was created with a class. So you just have to ensure that your models have different class names if you want to do it like that. Because we're going to do it like that, we can set the model name to be its class name. We'll get the model loss, which is just this value here. After it's been scaled, we'll turn it into a single value by taking .item. And then we'll go model.acc, or we'll get model_acc for the model's accuracy. We'll do the same thing here. Acc. I don't think we need to take the item because accuracy comes back in a different form. We'll find out. If in doubt, code it out. So calculate model 0 results on test dataset. And I want to let you know that you can create your own functions here to do almost whatever you want. I've just decided that this is going to be helpful for the models and the data that we're building. But keep that in mind that your models, your datasets might be different and will likely be different in the future. So you can create these functions for whatever use case you need. Model 0 results equals eval model. So we're just going to call our function that we've just created here. Model is going to equal model 0. the data loader is going to equal what? The test data loader, of course, because we want to evaluate it on the test data set. And we're going to send in our loss function, which is loss function that we assigned above just before our training loop. So if we come up here, our loss function is up here. And then if we go back down, we have our accuracy function is equal to our accuracy function. We just pass another function in there. Beautiful. And let's see if this works. Model 0 results. Did you see any typos? Likely. Or errors in our code? How do you think our model did? Well, let's find out. Ooh, there we go. We got model accuracy. You see how we could reuse this dictionary later on? So if we had model 1 results, model 2 results, we could use these dictionaries and compare them all together. So we've got our model name. Our version 0 of the model has an accuracy of 83.42 and a loss of 0.47 on the test data loader. Again, your numbers may be slightly different. They should be in the same realm, but if they're not the exact same, don't worry too much. If they're 20 accuracy points less and the loss is 10 times higher, then you should probably go back through your code and check if something is wrong. And I believe if we wanted to do a progress bar here, could we do that? TQDM. Let's have a look, eh? Oh, look at that. Progress bar, that's very nice. So that's nice and quick because it's only on 313 batches. It goes quite quick. So now, what's next? Well, we've built model 1. We've got a model 0, sorry. I'm getting ahead of myself. We've got a baseline here. We've got a way to evaluate our model. What's our workflow say? So we've got our data ready. We've done that. We've picked or built a model. We've picked a loss function. We've built an optimizer. We've created a training loop. We've fit the model to the data. We've made a prediction. We've evaluated the model using loss and accuracy. We could evaluate it by making some predictions, but we'll save that for later on, as in visualizing some predictions. I think we're up to improving through experimentation. So let's give that a go, hey? Do you recall that we trained model 0 on the CPU? How about we build model 1 and start to train it on the GPU? So in the next section, let's create number 5, is set up device agnostic code. So we've done this one together for using a GPU if there is one. So my challenge to you for the next video is to set up some device agnostic code. So you might have to go into Colab if you haven't got a GPU active, change runtime type to GPU. And then because it might restart the runtime, you might have to rerun all of the cells above so that we get our helper functions file back and the data and whatnot. So set up some device agnostic code and I'll see you in the next video.